There's no coffee, unfortunately, so we test the machine again when we found out that it still doesn't work. So we will have now upwards of 10. We are going to study the machine and see what's the problem and try to solve the issue. So we are sorry, for that. We have now 2 weeks of kind of trying to figure out what's going on, and I hopefully we will have coffee after the break. Anyway, so today it's a great pleasure to have Charlie Conroy here. I mean, everybody knows Charlie, I think. He's a professor here at Harvard. He did his undergrad studies in Berkeley and moved into Princeton for his PhD, where he finished in 2010. Then he actually came to Harvard, so he was a junior fellow of the Harvard Society of Fellows before going as an assistant professor to Santa Cruz. And then a few years ago, he came here. It's pretty amazing. I mean, I don't want to go through the whole CV of Charlie, so I just mentioned kind of what he's working on. I think he will talk about this basically during his talk. But I think it's pretty amazing because he has this overview over like dark matter and how galaxies form within dark matter halos. So really kind of on like cosmological scales, going all down to basically neutron stars and to a lot of stellar spectroscopy basically. And so everything in between at the moment, something that is really kind of hot in the group debated is the H3 survey, so a survey of halo stars around our galaxy. So anyway, I don't want to keep you from listening from Charlie, so please go ahead and talk about galaxies as a collection of stars.
Okay, great. Thanks, Sandro. Okay, so I wasn't quite sure what to say in this talk, honestly. Sandro and Erica gave me free rein, which was nice of them, but also a little overwhelming. So I thought it would be interesting to talk about galaxies as collections of stars. And what I mean by that is there's this connection between stellar physics, stellar atmosphere, stellar spectroscopy on the one hand, and what we think we know about galaxies on the other. And there are these kind of intertwined set of topics. You can't discuss one. Well, you can discuss stars without galaxies. I guess you can't discuss galaxies without stars. Anyway, so I wanted to give kind of an overview of at least my perspective of the state of the field, where some of the outstanding issues are, what are some of the successes, and highlight some recent results that we've been working on here. Please interrupt as we go along. I'd be happy to make this discussion where we get derailed by various things. And I'm the only person talking today, but in the vein of the sort of Battlestar theme we've had in the series, I was going to sort of battle myself in some sense. I'll present, after giving an introduction and some kind of motivation, I'll give kind of a pessimistic view of the field, and then I'll end with a more optimistic view, because that's the right way to do things, I think, end with the optimism. And much of the work that I'll describe, especially some of the results throughout the end, has been led by Joel Leja and Ben Johnson, who are postdocs here at the CFA.
Who's the optimist
Out of the two of me, or the two of them? Oh, that's an interesting question. I guess, yeah, you're right, absolutely. Yeah, sorry, Joel's the optimist and Ben's the pessimist. So maybe I'll channel each of them individually throughout the talk. Okay, so let's start with an overview of what we think we know about galaxies. The caveat there is, again, since we're talking about stars, we're going to ignore many other related fields, of course. We're going to ignore what we know about galaxies from dynamics, from explosions of exotic objects, about their gas, morphology, black holes, etc. So really focusing on the stellar radiation. And again, remember, when you look at a galaxy, the full energy distribution from the UV to the infrared, you're looking either directly at starlight or light that's been reprocessed from starlight. So in the optical, it's a lot of just raw starlight. Emission lines from H2 regions, of course, are originally from hot stars. And the dust is reprocessed stellar radiation. So one of the interesting results over the past decade has been studying the stellar mass function of galaxies and and its evolution and variation both with redshift and with galaxy type. So this is a really nice, there's been results that have come out since then, but this is a good example of, if you make a really killer figure, people will use it in talks for years. I think this is a really beautiful example of that. On the left is the evolution of the stellar mass function of star-forming galaxies out to redshift 1. And on the right is the evolution of quiescent galaxies to redshift 1. And one of the really striking results from this project was there's very little evolution, in fact, in the stellar mass function out to redshift 1. That's more than half the age of the universe. And on the right, there's very little evolution at the high mass end of the quiescent population, but a lot of evolution at the low mass end. Some of these results are debated in various contexts, but that's sort of one picture of where we stand in the field on that front. So that's what we can learn. One thing we can learn about if we know the stellar mass of a galaxy. On the star formation rate front, one of the sort of first order sort of quantifications of galaxy evolution is the cosmic star formation rate density evolution, sometimes called the McDowell diagram. So star formation rate per year per co-moving megaparsec in the universe is a function of redshift. This is where we get these buzzwords of cosmic noon in the peak of this diagram, cosmic dawn over here, and cosmic dusk. So it's just the evolution over time of the sort of intensity of star formation throughout the universe. And then as you go a little more refined, we start talking about scaling relations between different galaxy properties as insights to how galaxies assemble over time. This was one of the first diagrams of the so-called star-forming main sequence. It was, I think, before the era of stylistic plots, so it's a little it's a little opaque to read. But there's supposed to be those contours here, and there's a pretty tight sequence and correlation between star formation rate and stellar mass. This is from Jarle Brinkman in 2004. And then this really got kicked off in a new way by Kalinowski from the Deep 2 redshift survey, where this was mapped from low redshift up to redshift 1. And you see, again, a strong correlation between star formation rate and mass for what's called the star-forming sequence, and then the quiescent galaxies lie down here. And so understanding what sets the slope of that relation and its evolution over time, whether or not there is a single slope or a curvature in that slope, occupies a substantial volume of literature today. And then an even more refined question might be, what is the actual history of star formation for individual galaxies across cosmic time, not just their current star formation rates? That's been, I think, one of the holy grails in this field, because it, in principle, should tell you an awful lot about how galaxies grow. This is work from Joel, where he, in different redshift bins, took galaxies and binned them by whether or not they were on this star-forming sequence above or below, and computed the average star formation histories of those sequences. And you see what I think we expected to see, which is that quiescent galaxies have this falling star formation history over time. Galaxies on the main sequence of star formation, this green band here, have kind of a constant level of star formation, and ones that are above have this rising level of star formation. But you actually see it now in the data, which is pretty exciting, I think. There are other forms of scaling relations between, for example, the dust mass in the galaxy and the star formation rate, which gives clues as to the connection between star formation and dust and gas in galaxies. There's a whole industry of people measuring what's called the mass-metallicity relation, so the relation between stellar mass, or maybe luminosity, and the gas phase metallicity. So this is the famous plot from Christy Tremonti's paper in 2004 from Sloan. Jabran Zahid, who's a CFA fellow here, Clay fellow, has done this at redshift 1, and now people do this at other redshifts, and again, it's a whole industry. This is telling you the instantaneous snapshot of the chemical enrichment history of the galaxy, because the gas phase metallicity tells you about the instantaneous properties of the gas. There's a corresponding relation between mass and the stellar metallicity of the galaxy. This is harder to measure, so you see kind of a sort of a fuzzier relation. And this is in principle telling you about the integral of chemical evolution of the galaxy over time, because the stars retain memory of what happened in the history of the galaxy. Zooming in a little more in terms of sort of refinement, you can ask not just about the overall metal content of a galaxy, but how the metals are partitioned in different elements. And so this has been done for a while. This is something from my own work a couple years ago, looking at the ratios between the alpha elements of various kinds and iron in these funny logarithmic units where the sun is at 0, the solar abundance pattern. And you see as you go up in mass or velocity dispersion that the lighter alpha elements are more enhanced relative to iron, and this is interpreted as a change in the star formation rate timescale of a galaxy. So as galaxies form their stars over shorter and shorter timescales, you tend to get a greater ratio of alpha to iron peak elements. So this tells us something about, again, the assembly history of galaxies, and people are now working on measuring these relations out to redshift 1, 2, and beyond. And then finally, you can go all the way and connect the galaxies themselves to the underlying large-scale structure in the universe, the dark matter halos. This, of course, is much more difficult to measure. You can measure it dynamically in clusters or with satellite kinematics or lensing, or you can take statistical approaches to estimate that. This has become a whole industry as well, and the long story short is that there appears to be these fairly well-behaved relations between the baryonic content of galaxies and their dark matter content. So this allows you to sort of make a picture between the baryonic physics in galaxies and the larger scale cosmic environment. One of the fascinating things is there's these two separate power laws, and there's a lot of questions about what sets those slopes, what are the key physical relations. Some would say AGN here and supernova feedback here. and very little evolution with redshift, which is quite striking. So galaxies move along these relations, it seems. Right. So I'll emphasize here, and I'll say it again, I think, a few more times later. Everything I've mentioned are, of course, not observables. Right? You can't measure the stellar mass. You can't measure star formation rate. You can't measure metallicity. You measure photons, a spectrum, a photometry, and there are models that help you to translate those raw data into these physical quantities. And I'll come back to how that works in a minute. And then all of these relations are key factors in understanding how good state-of-the-art models are. So they're either used explicitly to calibrate the physics ingredients in stellar galaxy formation models, or they're used as tests, and constraints. So I'm playing to the audience here. These are all results from Illustris or Illustris TNG, but just to give you a point that any modern simulation or model of galaxy formation has to show that they can reproduce all these phenomena. So this is constraining reproducing the mass-metallicity relation, the cosmic star formation rate density, the star formation rate mass relation with various iterations of the Illustris model. This is the element or ratio distribution, the stellar mass-halo mass relation, and the stellar mass function. Right? So these things are key to making sense of the galaxy formation models and also helping to tune the various knobs that are the free parameters in those models. So these play a key role in helping us to understand how these complicated models are working. So that's just a quick overview of some of the physical parameters in galaxies that really depend on what we think stars are doing. Now I want to spend a few minutes building a little bit intuition of how we actually go about doing this in practice. So this is the field that's known as stellar population synthesis. Has a long history going back to at least Beatrice Tinsley in the 60s and 70s, who did a lot of the pioneering work. She has a wonderful review in 1980 that I highly recommend. It still is it's a wonderful article today. And again, this toolbox is critical both for taking your data and trying to turn it into something physical that you can then sort of tell a story about, and if you've got a simulation or a model, predicting observables, right? So it's this glue that goes back and forth. And I'll make a somewhat provocative claim that much of what we know about galaxy evolution fundamentally is dependent on the trifecta of stellar evolution, stellar atmospheres, and stellar spectra. There are other things as well, but I'll really focus on these in the talk. And so, you really have to understand what's going on at this level here to really make sense of or believe all of the stuff that's coming out of the galaxy world. So in a nutshell, I'll, in 2 slides, show you kind of how these models are built, and then we'll talk through a couple of the things you might want to worry about. The first, I like to give this as happening in 2 distinct steps. The first is building these sort of basic building blocks, these sort of basic underlying models. And for that, you need these three pillars. The first is the IMF, so how many stars are born as a function of mass. The second is where stars are at any given time in the HR diagram, which stars are still alive, which ones have died, have they evolved off the main sequence. So this is stellar evolution, or isochrones. And then at each point in this diagram, what does a star look like? So you need some model for what stars look like. And people will either take a library of synthetic models, like from Bob Caruso's work, or a library of empirical spectra, or a mix. Those are combined into these basic building blocks that are essentially single-age, single-metallicity models. You can think of them as like the theoretical analog of a star cluster. And then you take these building blocks and you add on 2 more things, or maybe 3 more things. Some model for dust, both dust attenuation or absorption in the UV and optical, and then re-radiation of that reprocessed light into the infrared. And then you need some prescription for the star formation history and the chemical evolution history of the system. So if you are a simulator or a modeler of galaxies, you typically take these as input sort of basic building blocks, and then your models predict both of these things. And then that allows you to make final predictions for what a galaxy should look like. So the full energy distribution is a function of wavelength. This is an example for dust-free and then with the reprocessing due to dust. So again, if you're a simulator, you predict these from your model, and then you use this stuff to turn it into the observable. If you're an observer, you measure this, you take your building blocks, and you try to sort of back infer what these things are.
Well, you measure that plus the molecules.
That's right. So I have a list somewhere. I thought of all the things that I ignore or I'm going to skip over. But yeah, there's a lot of other things that feed into this in principle that help constrain things. But a lot of what a lot of extragalactic observers do who are fitting just photometry, say, would measure this, take these building blocks, and then try to measure something about dust, something about the star formation history. And so that's the sort of, in one shot, the whole overview. Not the full story, so I can add molecules to the ellipses here, but there's a whole list of things, of course, that I won't talk about. Some of these things are, in fact, included in these state-of-the-art models. Some of them are not. And this is part of the story of why one should be at least cautious about interpreting some of the results, because there's a whole lot. If you think about a real galaxy, there's a lot going on that we are not capturing in the models. Then you can ask, once you have these models, you can ask some basic questions to kind of build your sort of mental framework for what's happening. If you take a galaxy that looks like this, full of old stars, and you ask where is the light coming from different stellar phases as a function of wavelength, what you see, for example, is that in the UV, you're dominated by these hot evolved stars, post-asymptotic giant branch stars and horizontal branch stars. This stellar phase is very uncertain, and so that should signal to you that this wavelength range carries a lot of uncertainties in the data of these types of systems. And that can be good or bad depending on what your interests are. In the rest frame optical, you're dominated by main sequence stars, and that's a good thing because of all stellar phases, we think we understand the evolution of the main sequence the best. And so it's kind of a fortunate coincidence that that's where we can observe often a lot of galaxies in the rest frame optical. We have access to those main sequence stars. And then as you go redder, you're dominated by the cooler evolved stars, including the red giant branch, and this the sort of unfortunate asymptotic giant branch. I say unfortunate because we'll see, it carries many uncertainties, but it can dominate the light or contribute substantially to the infrared light for younger populations. So the red line here is what you would see in this galaxy if it was at redshift 2, where now this AGB phase contributes a huge amount of the flux. For a galaxy more like the Milky Way, or one with a slightly rising star formation history that you might see at higher redshift, you see the main sequence dominates the flux almost everywhere in the optical and the UV. That you would think is a good thing from what I said a moment ago, except that the stars that are actually dominating this part of the light are really the very highest mass stars, these 20, 40, 60 solar mass stars. And those are also very uncertain, so it kind of bites you on both ends. And then as you go, again, redder, you have this important contribution from these evolved cool stars, which are challenging to model. Okay? And we'll see why that matters in a moment. You can also just ask the question, if I look at a galaxy like the Milky Way, say, what is the light-weighted average age? So what is the average age I'm looking at every wavelength? And it goes from being very young, if you look at the ionizing spectrum, which makes sense, because those are all contributing from very hot stars, which are short-lived. A large change in the average age as you go through the UV, and then a modest change as you go into the optical, and then very little change as you go from, say, half a micron to 2 microns. So not a big change, actually. And so there's pros and cons to this basic fact, but it's a kind of key point in understanding galaxies. The pro is that with a wide wavelength baseline, if you had data that goes from here to here, then you could actually reconstruct the recent star formation history pretty accurately, because you have a lot of age sensitivity to the intermediate and young population. The con is that the sort of downside is that it's difficult to measure the old underlying population. It's just a standard problem with stellar population models that even if half the mass is in an ancient population, it contributes a small amount of flux, and so that, by sort of definition, makes it difficult to measure. And that's problematic. That's where most of the mass is. And right on cue, the initial mass function is this other, huge input ingredient that carries all this, emotional baggage for me, and is very challenging to measure. So this is an example of a few, commonly discussed types of initial mass functions. So again, number versus mass. You can then ask, say, for the Milky Way IMF, so what's been measured in the Milky Way disk, what is the cumulative mass contribution from stars below a certain mass for an old population? And stars less massive than half a solar mass contribute about half the mass. So all the mass to first order in the galaxies in those low mass stars, but they contribute a few percent of the light. This is the cumulative luminosity contribution as a function of mass. And so this is just a regurgitation of this standard thing that the light is dominated by the most massive living stars in a galaxy. And yet those stars contribute a very small fraction of the mass. And so in order to understand the stellar mass of a galaxy, you have to assume a functional form of this. And we make this crazy assumption that this single form in the Milky Way applies to all galaxies through all time and all environments. And in part we do it because we have to, because it's so hard to measure those lower mass stars. Yeah?
When you say light here, you mean in what wavelength or the entire line?
All wavelengths. There's no wavelength range where these low mass stars contribute a substantial amount of flux. Because they are cool stars, you might think as you go redder, it's better. And it helps a little bit, but then you're dominated by the red giant branch anyway. So you always have higher mass stars that are outshining you in every temperature region, either the main sequence or the red giant branch. Nonetheless, though, so it's not completely hopeless. Like this number here is a few percent, it's not 0. And that actually is a big difference. If you just ask, like, how sensitive is the spectrum of an old galaxy to the IMF in kind of a heuristic way, you see, in fact, there are features that are uniquely sensitive to those low mass stars. And there's a whole industry that tries to measure these features in order to measure those low mass stars. So it's possible, but it's hard work. And you see the y-axis here. This is a change of a few percent. And this is the difference between a Milky Way IMF and a very, very steep IMF. So it's a subtle game, but in principle, the information is there. And so we should work hard to build models to try to extract that signature. If you then go on to ask, like, what can we measure about the elements in galaxies? This is an example spectrum, it's a model of an elliptical galaxy, an old population, at a velocity dispersion of 350 kilometers per second, which is typical for a big, massive elliptical. And I'll just note, sort of in passing, this is where the true continuum would be for this spectrum, if you could, for example, resolve out the individual lines perfectly. And so the difference between this and this is telling you that there's just a forest of atomic and molecular absorption lines, which smooths out the which makes the continuum, the pseudo-continuum, much lower. So you're never seeing continuum photons in a galaxy. So that should be a sort of a cautionary note. If you ask, like, where could I measure different elements in the spectrum, if I just change the abundance of nitrogen or carbon by a factor of 2, I would induce a 10 to 20% change in the spectrum. Calcium would induce 10% change, iron a few percent change, but it's all over the place. And so you can measure each of these elements independently because, as you see, the signal is not 0. In fact, it's moderately strong. And the signatures are different for each element. So you can separately measure all these pieces. So that's good. And then finally, you can learn a lot about the dust, especially if you have the full wavelength coverage from the UV to the infrared. So these are just panels where you vary one component of the dust at a time. This is changing the dust temperature. So you see the peak of the infrared SED is shifting. If you vary the composition of the grains, what that does is it changes the resulting extinction curve, which changes the amount of absorption as a function of wavelength. So it changes mostly the UV here. But the total dust mass just changes the overall amount of optical depth, and so it changes both the UV and the infrared. And the grain composition again, so when you change the amount of pH molecules, then you change the pH bands here. So again, with enough data, you could separately imagine measuring all these things. So in principle, if we had, wonderful, perfect data and perfect models, you could imagine measuring all of these things. You could imagine measuring the full star formation history of each galaxy in many different age bins. You can measure the metallicity and its whole history through its evolution, the abundances of at least 15 different elements, the initial mass function, properties of the H2 regions based on the nebular lines, the properties of the dust, and even the star-dust geometry. So if you had that for every galaxy, you would know an incredible amount about galaxy evolution, and you'd be sort of soaking as much possible information out of the data as you could. And so, the fundamental goal of the stellar population field is to measure all of these things, or at least make progress toward measuring all these things. That's kind of the high-level goal. Okay, so now I'll give the pessimistic view of this field. So my summary diagram of this, and I'll start with the summary first, so you have it in your head. If you imagine a diagram showing age kind of schematically here and wavelength here, as I said, in this part of the diagram, you're dominated by massive stars. Their lifetimes are uncertain, their properties are uncertain. This whole wavelength range here, you're scattered with nebular emission features, both continuum and line. Here, you're dominated by absorption from dust. Here, that dust is re-radiated in the infrared. You have cool evolved stars, which contribute a lot of flux in this region here. You have these hot evolved stars, which are difficult to model and dominate the flux down here. Circumstellar dust from evolved stars play a role here. And this is the sweet spot. So this is where a lot of people spend a lot of time, like elliptical galaxies in the rest frame optical, where you can really learn a lot of information because relative to everything else, they're a fairly straightforward population to model, we think. And relatively speaking. So the way you could think about the two key problems, the way I think about them is that the first problem you have to deal with is that the main sort of first order effects on the galaxy spectrum are very uncertain. And those can be split into two pieces. First is the starlight is dominated by either massive evolved stars in the sort of blue or UV, or evolved cool stars. And both of those aspects carry substantial uncertainties at the present day in stellar evolution models. So that's a problem. And then on the dust side, which have an order unity effect as well in redistributing the energy, it's difficult to predict anything about the dust. That's maybe too strong of a statement, but the dust is a tricky beast, and so that's pretty hard to get around. And then the second problem is that all the other second order things, like the IMF, the old-Teller pops, the element abundance ratios, they have second order effects on the spectrum, but relative to the first, these aspects are actually fairly well understood. You know, the low mass stars are better understood than the high mass stars typically. The effects of element abundances on the spectrum is fairly well understood. So these are in fact better understood, I think, overall, but the signal is small. So they're harder to measure in that sense. So that's kind of the one way of thinking about the problem. Yeah?
Well, I was just going to ask about the nuclear contribution. If you think the galaxies merge at some point and that merger turns on for some time, the AGN, because of the dust, that seems to me to be something that's going to complicate that.
Absolutely. Yeah, so early on, I tried to delineate things I was going to leave aside just because of lack of time. But the absolute AGN is another problem that impacts not only the line ratios, but the overall energy distribution, the ultraviolet in principle, the mid-infrared. So it's a whole other can of worms, absolutely. Yeah.
I wouldn't imagine that you hadn't had the same goal.
Okay. All right, fair enough. Again, to understand the energy distribution from galaxies, you need to understand literally all phases of evolution of stars at all metallicities. And that's bad because we don't understand any phase of evolution of any star perfectly, not even the sun. So that's a problem. I'll give you two examples of this. These asymptotic giant branch stars, which can dominate the flux from in the infrared, their lifetimes are uncertain by at least a factor of 2. This is the luminosity function of these such stars in the small and large Magellanic clouds in the infrared. Black is the data, and red are three different stellar evolution models that all agree with the optical color magnitude diagrams. So they've been constrained already to reproduce the optical CMDs, and you see they predict, more than factor of 2 variations out here actually, and no model reproduces both the small and large Magellanic clouds. So this is there was a paper on the archive just I think today or yesterday about this. It's an ongoing active area of research. It has to do with how you treat mass loss in these stars, how you treat internal mixing processes, all these things which are intrinsically three-dimensional processes you have to sort of cram into a one-dimensional model. It's very hard, and clearly the state of the art is a little bit lacking. Zooming to the high mass end, massive star lifetimes are uncertain by at least 30%, probably more like a factor of 2 or more. This is just one example. The effects of rotation on a star can, in principle, enhance its lifetime because mixing drives more fuel to the core, which means the main sequence lifetime is longer. This is the change in the lifetime of a star between rotating and non-rotating as a function of mass for 2 different prescriptions for rotation. One from the MESA model that we've been developing, and one from the Geneva group here. And it's just different assumptions about how you do the mixing in this one-dimensional model. You have several free parameters for how that mixing happens. And it's uncertain, and it's not well calibrated on observations. And that's just one of many uncertainties that affect the massive star lifetimes. Stellar rotation also affects just the broadband color evolution of galaxies. This is differences between rotating and non-rotating stellar models in the U-B and B-V color evolution over 10 megayears. And you see huge differences in the colors between rotating and non-rotating models. Furthermore, the rotation and stellar binarity affect the ionizing continuum from galaxies, or just from stellar populations. which will in turn affect the nebular emission lines and other things. This is a diagram of the ionizing luminosity of hydrogen and ionized helium over time. The colored lines are our own models as a function of rotation rate, and then the gray dashed line is a binary evolution model. And you see, especially at later times, factors of 2 to 10 changes in the ionizing continuum. So it's a huge source of uncertainty in interpreting nebular emission lines of galaxies. I'm going to skip over, I apologize to Igor, but I'm going to skip over the issues with empirical spectral library just because I want to kind of get to some discussion toward the end. If you look at a galaxy, again, you see all these sort of nice, smooth features that those of us who look at galaxies are used to seeing. And we have these labels for these different fairly strong features. But it's really important to remember that as you zoom in on a little patch of a spectrum, it looks like this. It's been smoothed by the Doppler motions of the stars in the galaxy. And for massive galaxies, that smoothing is very substantial. If you could magically turn off that broadening kernel, and look at a little 10-angstrom patch, you would in fact see all of these individual transitions of atoms and molecules. And so you look at one little blip here, it's actually comprised of many transitions. And that's challenging because it's hard to model theoretical spectra ab initio from first principles. This is a plot from Bob Caruso, who spent many years trying to work and improve the atomic and molecular line lists. And it is much improved over 30 years ago, probably, I would say. Yes, I hope so. But there are still disagreements. And those things add up in a cumulative way when you smooth this 10-angstrom chunk to a whole galaxy. This is a comparison between the observed solar spectrum and a model here. And there are many factors that affect things that you have to take into account, not only just the lineless parameters, but the effects of magnetic fields and non-LTE and 3D and rotation, and it's obviously its own field. It's very complicated. But it can have a big integrated effect on the whole system. This is just one example. Atomic and molecular lines come in two flavors, one which we've measured in the lab, and we know the parameters pretty well, and ones which are just predicted ab initio from approximate quantum mechanic calculations. If you turn on and off those predicted lines, this is the change in the spectrum of a solar-type star, from the sort of blue to the red, and it can induce a 5 to 10% change in the spectrum just from these very uncertain atomic and molecular lines. So that's just one of like half a dozen different issues that you have to worry about when thinking about modeling stellar spectra. And then the effect of the corona is also substantial and is never modeled in galaxies, but stars like the sun and others have a hot corona. And if you turn the corona on or off in a model spectrum, again, it will strongly affect the UV between 10% and a factor of 2. This is just for the sun, but other types of stars as well have corona. And those are never included in stellar models, at least to my knowledge. Then, sort of zooming out a little bit, so that's like really fine-grained. Zooming out a little bit, you might say, like, well, does that actually matter at all? The short answer is I don't really know. But here's an example of like what you might want to be worried about. So there's tension, it turns out, between taking these sort of population models, applying them to galaxies to infer the star formation histories on the one hand, and on the other hand, taking what we think are kind of at least our best guess of how to do this, which is actually getting resolved star CMDs, chromatic diagrams, and inferring the history of star formation directly from the resolved stars. That's like as good as we can imagine doing. And if you try those two techniques on the same data, you get different answers. That's what's shown here. So if you look at the left plot, it's a little simpler version of this. This is kind of funny units, but it's basically the cumulative history of star formation as a function of age for small, like dwarf galaxy-type systems. Because we can't do CMD reconstruction for more distant, massive galaxies because stellar crowding makes that impossible. So for nearby galaxies where the stars are kind of spread out, you can do this. This is the history of star formation for the dwarf measured from the CMD, which again we think is ground truth. This is the stellar population-based techniques. So like totally different. Like in the same plot as being shown here, basically, this is the same data on black points. The background points are the history of star formation for galaxies of different mass. And one way of looking at it is that the dwarf reconstruction from a CMD looks like a massive elliptical if you did stellar population modeling. So that's a huge red flag. And we should, frankly, have all stopped 7 years ago and solve this problem before going forward, because this is like a big red flag. And then finally, this is a kind of heroic work by Danilo from 2009, where he ran like 20 different permutations of these models and ran them all the way through to compute stellar mass functions, and plotted what he got. And you see each color is a different mass function from like one set of model assumptions, different codes, different IMFs, different metallicities, blah 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 blah. And you see that there's a factor of 10 spread in the number density of objects depending on the code. So that's also alarming. That's the end of the pessimistic section. I'll end in 5 minutes or so giving some optimistic views about all this, because that all sounds pretty depressing. But there's some magic that happens that we don't, I think, understand, but that gives us hope that this is not just a fool's errand. So one thing you can do is you can just say, I'm going to try to measure masses and very different codes and very different, this is like fitting techniques, very different underlying physics, very different treatments of dust and so on. And in fact, the resulting masses come out very similar, less than 0.1 dex variations when you do things carefully. Okay, so that's one. So actually, in spite of the last figure, I would argue that stellar masses are remarkably robust, and we can talk about why that is in a moment. But they seem somehow immune, by and large, to most of the sort of nitty-gritty details. Second, you can do a lot of, so what we can't do is sort of perfect ab initio calculations. If we had, again, perfect stellar models and perfect everything, we could just go forward and we'd all be fine. So we can't do that, and so instead we have to come up with sort of consistency checks to figure out, to convince ourselves that we're at least not going down a dark alley. So one thing you can do, one thing that Joel did recently, is compare the stellar mass that you derive to the dynamical mass. Now, these are totally separate quantities, and in principle, you could imagine them being scattered throughout this whole diagram. Obviously, if they were in this part of the diagram, that'd be very bad, because it would mean the mass you estimate from the stars is greater than the dynamical mass. That's a no-go. And it's really encouraging that stars, or the galaxies, are happily lie up right up against that line, but don't go beyond it. It can be down here, no problem, because you can have other forms of mass, gas mass, dark matter mass, etc. So this is actually, this is one of these things where it's a really nice consistency check when you see that that works. You can also compare different indicators of star formation in a galaxy, the UV flux, the H-alpha flux, infrared flux. And for most galaxies, the agreement is pretty good, again, within a factor of 2 or so, just sort of out of the gate. So, in fact, these different ways of estimating star formation rates tend to work out okay. There's another consistency check. And this diagram's a little bit complicated, but the basic point is that you can imagine taking the Maddow diagram, the star formation rate versus redshift, and integrating it. Well, don't integrate it. Take the star formation rate evolution and compare it with the derivative of the mass evolution. Those should be the same, right? Because any stars that are being made are to be made in star formation. And so if you compare two epochs, the star formation between those epochs should equal the dm/dt. And so this is the comparison between the density of star formation and m dot versus redshift. This was the state of the art over the last 5 or 10 years. There was this factor of 2 discrepancy between those two techniques, and that was a kind of another red flag. Like, those should agree, they weren't, for a variety of reasons. Some of the work that Joel and Ben have been doing with more updated details and all kinds of things they can explain to you later, kind of takes away that factor of 2 offset. So we think we have a model that's at least self-consistent now in the star formation rates that are being derived and the stellar masses. But it does mean a factor of 2 change in something, either the masses or the star formation rates. So to the simulators, that matters, right? A factor of 2 change in things is going to change the calibrations. I'm going to skip that one. You can also actually measure properties about the dust. So with enough data, so Mariska and I from a couple years ago measured actually the slope of the extinction curve and the strength of the ultraviolet bump that's the strongest feature in the extinction curve. And so we measure that galaxy by galaxy and compare it to like the Milky Way and other forms of the extinction curve. So again, with good enough data, you don't have to just assume a curve. You can actually measure it self-consistently in the data. And then finally, there was this nice work that Ben had done a couple years ago where you basically take nearby dwarf galaxies where you have good car magnitude diagrams. You measure the star space histories, which gives us kind of ground truth. Use those to predict the photometry you should measure from those systems, and then compare it to the actual observed photometry. And that's what you get here for a sample of dwarf galaxies, where the predicted compared to the observed is within about 25% over the entire UV optical range. There's interesting tension we don't understand in the infrared, but in the UV optical at least, there's nice consistency between the predicted and observed CMD-based star formation histories. That doesn't resolve that earlier tension I was describing, but it's at least one form of a consistency check. So this is what we're left to do, and this is the challenge of this field, is that we have to look for these kind of indirect consistency checks to kind of see what we're doing, and if we know what we're doing correctly. We have a hard time with finding real ground truth we can grab onto, and so we have to do these sort of more indirect tests to see if we're on the right track. And with this whole set of indirect tests I was describing, it does suggest that at least within a factor of 2, many of the physical properties we are interested in, masses, star formation rates, metallicities, are in agreement. So I'll end with a summary, and then we can have some discussion here as well. So the basic point is that this technique is good for measuring physical properties of galaxies, but it relies on many ingredients sort of at the lower level. Stars of various aspects, dust, the IMF, and et cetera. And despite, essentially ubiquitous use, these codes have exploded in popularity in the past 2 decades, they're really, frankly, not well calibrated over most important areas of parameter space. And systematic uncertainties could be almost anywhere, including knowns and the unknown unknowns. And yet, I think it's not actually fully understood why things work as well as they do, but by some magical, sort of grace of God, these codes seem to do actually pretty well, at least at the factor of 2 level. And so a lot of focus over the past couple of years has been devoted to breaking this factor of 2 barrier. Because in fact, there are a lot of questions that hinge on, say, stellar masses or star formation rates that are more accurate than a factor of 2. If you think about the dark matter content in galaxies, if you get the stellar mass wrong by a factor of 2, you go from being a dark matter-dominated galaxy in many cases to a dark matter-free galaxy. So there's a lot of questions that really depend critically on pushing beyond this factor of 2 barrier. And that's where a lot of the ongoing effort is in this field, and I think I'm optimistic that we'll make some progress. Okay, thanks.
Okay, so we have like 10-15 minutes for discussion. So yeah.
I guess this is just a comment, but probably one of the reasons it works within a factor of 2 is you get to the large sizes. And the reason I mention that is that you would think that the smaller sizes would be easier, smaller things that are easier to figure out using a solar calculation synthesis like other clusters. But in fact, there's another issue that one of the things you left out, which is the horizontal branch and metal core systems. It's not something you can predict. So when you get to a very large system, it doesn't really matter anymore because those kinds of stars are a minority, I suppose. And again, they affect the UV part of the spectrum, but somehow magically it all gets washed out for a larger system.
Yeah, so, okay, great. That gives me a chance to talk about globular clusters. Because I wasn't talking about in the main part is because it was too much to talk about already. But, right, so globular clusters historically have been used as a calibration of this technique because in principle, you have these star clusters that are a single age and a single metallicity, and they're sitting there, and they're great tests of this. And that was the classic lore, and people would build their models and try to compare them to those observations. But it turns out that globular clusters are terrible calibrators for these models because they have so many interesting things going on their own, like a large population of hot horizontal branch stars, like very unusual chemistry that shows large variations in helium content and oxygen abundance. For the lower mass globulars, you worry also about stochastic effects on the evolved stars. We only have a couple stars, and so it doesn't look like a fully populated IMF. And so, yeah, it's kind of just by coincidence or luck that those complexities don't seem to be as prominent in galaxy-wide populations, which is good. The downside is it makes it then more difficult for us to figure out how to calibrate the models because the clusters are no longer straightforward tests, I would say.
And that's why you're doing 67, which you didn't have time to talk about.
Right, yeah, so I'll just show it now. Yeah, so everyone should know M67. It's a great cluster. So this is an example of fitting the spectrum of M67, comparing the observed model-based constraints. The model constraints from the quote-unquote observations, which is just the actual measurements of individual stars. And we get the age about right, and the metallicities we get all about right. So that's a kind of a test of the ability to measure abundance ratios of these clusters. This is a globular cluster where there's not even agreement in the literature between different groups who do individual star work. So it's like, we agree, sort of, but it's not clear what that means. Yeah.
What would be the best observational approach to pin down the rotation issue on that star? Is there a sort of observation that you use to constrain the model? Because 20% change in lifetime, I don't know where you can see that.
So Seth Gossage, who's sitting in the back there, is a grad student in the group working on rotating stellar models. And you should be able to see it in intermediate age or to young open clusters in which these, not the very most massive stars, but the sort of intermediate mass stars should display a range of rotations. And Andrea, who's doing the observational work on stellar rotation in the Magellanic Clouds, right? So there's these populated intermediate age clusters in the clouds where you should get a constraint on the rotation rates and the distribution of rotations of stars on and near the main sequence. So that's one good place to look. Well, you can measure the velocity broadening in the spectrum. That gives you a constraint on that technique. But it's hard. But that's one place to do this. Tony, and then Michelle.
So some years ago, the IMF of the Milky Way was the saltpeter IMF, and now it's not anymore. What happened there?
Well, do you mean like what happened between saltpeter's work and subsequent work?
Yeah.
Well, so saltpeter never measured the mass. He measured it, I think, between a half and like 2 solar masses, I think. So he never measured it below a half. And then with, I think, Hipparcos, where they had distances to those lower mass stars, they measured the turnover. But if you actually look at the actual data on constraints of the IMF throughout the galaxy, there's a lot of scatter because it's very hard to measure. I haven't seen work using Gaia to redo this, but I presume someone's doing it, so that should be much better. The challenge with the IMF is that we can measure it pretty well in one environment, which is the solar neighborhood, and any theorist would tell you, and now maybe you don't want to believe a theorist, but anyone would tell you that there's got to be some variation of the characteristic mass with something. Metallicity, pressure, density, temperature, like any way you try to frame a theory for the IMF in its shape, you think it should depend on something. And as you go to different types of galaxies, different redshifts, the typical characteristics of the ISM change, so you kind of naturally expect some variation. But, and so we've reported some evidence for variation in the centers of massive ellipticals. Some people have measured some variation in ultra-faint dwarf galaxies, but it's very hard and it's very subtle work. So hopefully that's an area where next generation telescopes will help a lot, I think. Jamil?
Okay, so excellent that you had this question, because I actually also wanted to ask about the IMF and beyond the Milky Way. So what are the perspectives on using these models to constrain crazy IMFs like first stars or very low metallicity systems? I mean, I understand there's lots of uncertainties, but maybe we can at least rule out some of the possibilities.
Right, so on the sort of low metallicity, sort of early star formation end of things, there's been a bunch of work using HST to measure, by star counts, the mass function in nearby dwarf galaxies, down to about, I think, 0.3 solar masses as faint as they've gone. And there's been some evidence for a more shallow IMF, which goes kind of in the direction of the sort of Jeans mass thinking would take you. But it's very hard work because there aren't many stars down there. And so I think it's a thing that JWST will be able to really clean up on. For the more distant galaxies, like the big ellipticals, you'll never be able to individually resolve stars in the centers of those galaxies, like ever. At least not the low mass stars. And so you have to use these kinds of models to make progress. And that's what we've done over the past, I don't know, like 10 years. And we've found evidence for, and people have found evidence from distinct techniques like with dynamics and lensing, that the IMF becomes more bottom heavy, more low mass stars as you go to the centers of these very massive ellipticals. So that's the sort of standing result there. Igor?
When you fit spectra of galaxies, especially if you do it to like normal stuff, not super alpha enhanced and so on, it looks great. Like chi-square is close to 1 if you have the propagation of errors from spectroscopy and so on and so forth. Then you're trying to fit a high signal to noise, high resolution stellar spectrum using the most advanced stellar atmospheric models, and you get chi-square of 30 for a red giant. And then how does it happen that at the end you average those stars where you have like signal wearing up this signal chi-square of 30 into dwarf galaxies which have not so high velocity dispersion? So as we talk about comparable resolution, you end up with models that correspond to what we see from the stars that don't correspond to what we see.
Good question. So what we don't do, and I think there must, I can't generalize too much, I suppose, but if you took those theoretical models, which I agree, even the best theoretical models, if you applied them to real stars, they don't match up very well, especially as you go to cooler stars. If you took those theoretical models and built machinery in this capacity with those models, I don't know what would happen, but I suspect you would find
worse.
Right, so it wouldn't be good. So as you know, what we do instead in this field is we use empirical libraries of stars as the backbone, and then we graft onto those empirical stars the synthetic models. So we only use the synthetic models differentially. And so it's kind of like a Taylor expansion, so you're off kind of in second order, not first order, in terms of any errors in the synthetic models. So I think that's the best answer I can give you. We don't use the synthetic models like straight out of the box. We only use them to differentially correct the empirical models. And so the empirical models have whatever physics the universe decided to make in them. The challenge there, as you know, is that you have to have good coverage in all of the relevant stellar parameters, and that's the challenge.
Yeah, and the stellar parameters is another problem.
Yeah.
You showed this picture briefly with the global cluster where there's disagreement on measurements by teams from individual
Yeah.
people doing individual stars. You know, there's this standard candle, like not candle, but whatever, the gold standard in stellar spectroscopy that they're trying to promote the Gaia benchmark stars.
Mm-hmm.
So if you look at metallicities obtained from Gaia benchmark stars by different groups, they have a spread of like 0.15 dex. We had this long discussion about this at the latest Stellar Library workshop in Brazil like 2 years ago. And basically with the current state of the art in the determination of atmospheric parameters, it makes no sense to obtain stellar spectral with signal to noise of greater than 50 because you are not limited by the signal to noise of your spectrum, you are limited by the approach you take.
Yeah.
So what would be your comment about this?
That's a good point to raise. I think it's, I don't know, is what I would say. I think that could be a slide in the pessimist column, but then somehow it kind of, at least for MC7, it kind of works. Now, whether or not it works better than a 0.1 dex, I don't know, but it just works. And I don't know if it's because we happen to choose the right set of parameters. I think that's probably unlikely, because what are the odds? Or maybe there's some averaging effect that happens when you include many different stars. I don't know. But that's another outstanding issue, is that we don't even know the metallicities of real stars in the solar neighborhood to better than 50% or something. And so it's hard to then use a much larger library of stars as empirical templates when you don't know their parameters exactly.
If you remember when solar metallicity went to minus 0.3 dex a few years ago.
Mm-hmm. Yeah. I mean, the oxygen abundance in the sun is still a matter of controversy. All right, maybe one last question, and we'll wrap up.
Yeah, so I mean, thanks for a great talk, and despite the sort of long pessimist section, which was longer than the optimist section, I gotta point out you and your group have been making sort of amazing progress on a problem that's got all of these open questions. So just kind of philosophically, how do we decide which of those aspects to address? And as we address them, how do we decide what the current best model is to move forward with? seems like the more we add to each sort of corner of the problem, in a sense that opens up a variety of options for how we might treat parameter or whatever.
Yeah, I suppose if I had a good answer to that question, we might have made even more progress by now. Because it's.
I guess what I'm saying is that we seem to be making progress on this problem, even though there's a lot of open aspects. So how do we sort of navigate our course through it?
I don't know. I mean, it really is. In some ways, it's almost a little misleading to have this field have like a single, simple title of population synthesis, because it really is many fields coming together in kind of a superfield of galaxies. And so it really is like the case that you have to solve, or at least retire the risks in many different areas of astrophysics. And it's even difficult to sometimes identify what are the, if you could ask me to like list what are the key top 5 uncertainties, and it's like it's hard to do that because it depends so much on the kind of data you have and the kind of galaxy you have, right? If we're talking about an old elliptical galaxy, it's a very different set of a list of the top 3 issues than a high redshift star-forming galaxy, because they're emphasizing different corners of that two-dimensional diagram I was outlining. So if you want to do everything, which is what kind of we try to do, then you have to solve everything. If you are focused on a certain subset of the problem, I mean, this is one of the reasons why historically there's been this whole little subfield that's focused exclusively on quiescent galaxies, because it proposes a very kind of neat subset of the problem in which you can, you're mostly wrangling with, line lists and things, and not so much with binarity and massive stars. So, and that's the course that many people often take in the field, is they have one science aim, say, they want to understand redshift 10 galaxies, and then they build models that focus on that part of the problem. And I don't know, I enjoy seeing the connections between the different pieces, but it does mean you have to then solve everything at the same time.
Okay, so let's thank Charlie again.